Hello, everyone. I am Bowen Yu from Tsinghua University. I'm glad to be here to present our work. Before diving into details, let's introduce some background knowledge about big data, Spark, and distributed machine learning in Spark. The development of Internet demands processing unprecedented amount of data that traditional analytical databases cannot handle, which is called big data. The big data challenge motivates a stack of open source frameworks like Hadoop and Spark. Nowadays, those systems are widely deployed to extract values from big data. Spark is an important framework that unifies big data analytics. Domain-specific libraries are built upon Spark's core module using its RDD API. Spark officially includes libraries for graph computing, machine learning, structured data analytics, and stream processing. Then let's discuss the distributed machine learning training in Spark. Conventionally, distributed machine learning is based on MPI, in which a group of processes symmetrically compute and actively communicate with each other with collective communication. In the case of distributed machine learning, all reduce is typically used for collective communication. Spark, on the other hand, adopts a driver-executor model in which a driver program runs on a single node and offloads the parallel paths to the executors. This pattern is similar to fork join. In the case of distributed machine learning, tasks together with its context are broadcasted to executor for distributed execution. Then an aggregation combines the gradients and sends it to the driver for parameter update. The advantage of Spark's model is threefold. First, it provides resiliency against frequent failures in commodity clusters. Commodity clusters are the de facto configuration for big data processing. Second, it provides auto-scaling for better cluster utilization. Third, it provides single-thread abstraction to ease programming and relieve users from the complexity of parallel programming. Despite training machine learning model in Spark has advantages, it has scalability issue. The motivation is based on empirical finding under two platforms. First, a 448-core in-house cluster named BIC, and second, a 960-core public cloud cluster named AWS. We benchmark MLlib's three machine learning models, LDA, LR, and SVM. 6 real-world datasets from libSVM and USI are chosen. Despite the resiliency from Spark-based distributed machine learning, we observe a scalability issue in MLlib, which is an official machine learning library of Spark. The speedup of 8 machines to 1 machine are reported in the chart. From the chart, we can see that the scalability of MLlib is quite unsatisfactory. The average speedup is only 1.25 times, and the highest speedup is only 2.49 times. We are interested, what is the hotspot that limits its scalability? Diving into the history log, we decompose the wall clock time into 3 parts at the scale of 8 nodes: aggregation, non-aggregation, and driver. The driver represents accumulated time of computation not offloaded to the executors. The non-aggregation represents the accumulated time of other stages. The aggregation represents accumulated time of stages related to aggregation operation. We can observe that aggregation is a significant hotspot, which is responsible for 67% of the wall clock time. Aggregation can be further divided into computation and reduction. From the strong scalability of LDAM, its reduction time increases with the increasing of number of core, which shows that reduction is the scalability bottleneck. What is the cause of poor reduction scalability? Currently, Spark is using a tree-based reduction algorithm. However, in the case of machine learning, reduction typically performs on large objects like gradient vectors, making the tree-based algorithm not optimal. For example, the ring-based algorithm followed by a gather fits well with machine learning reduction, which is shown by theoretical complexity analysis. So, an immediate solution would be implementing ring-based reduction algorithm in Spark, but unfortunately, the aggregation interface of Spark prohibits scalable reduction algorithm. Let's see the aggregation interface of Spark. Although this interface is enough to implement tree-based reduction, its problem is that the aggregator is an object, which we have no idea how to split. This prevents the ring-based algorithm because it relies on the splitability of aggregators. Then we will present Sparker's design. Sparker focuses on three challenges. First, aggregation interface should include aggregator splitting semantics. Second, low latency communication among executors is required. Third, communication amount should be reduced. To overcome the first challenge, we designed a more general aggregation interface named Splittable Aggregation Interface. Compared to Spark's aggregation interface, the aggregator splitting semantic is included in the Splittable Aggregation Interface. The split up is a function that splits an aggregator and gets a segment of specified index. The concat op is a function that concatenates a sequence of segments back to the results. This figure sketches the algorithm behind the splittable aggregation interface. Thanks to the aggregator splitting semantic, the aggregator can be split into multiple segments so that more scalable reduction can be applied. How to provide inter-executor communication? A low-hanging fruit would be reusing Block Manager, which is a shared object storage inside Spark. However, it has very high latency, as this figure suggests. Thus, we implemented a low-latency inter-executor communication module named Scalable Communicator based on 0MQ and integrated into Spark. It directly provides an explicit message passing abstraction, which enables lower latency because it eliminates the overhead from shared object storage abstraction. Note that Scalable Communicator only provides neighborhood communication on a ring-based topology, which is enough to support ring-based reduction. We made several improvements on Scalable Communicator. First, multiple parallel communication channels are established between neighboring executors. There is dedicated thread for each communication channel in the executor. This topology is called parallel-directed ring. Its advantage is that it provides abundant CPU power to overcome the large CPU overhead of Java serialization deserialization in Spark. Second, how executors are placed into the machine is important. If executors are improperly placed, communication channels are all internode communication. Internode communication has limited bandwidth and higher latency. With topology awareness, the amount of internode communication is greatly reduced. In this example, the amount of internode communication is reduced for 4 times. Based on the splittable aggregation interface and the scalable communicator, we implement a ring-based reduction algorithm as this figure illustrates. To perform ring-based reduction on 4 executors, 3 iterations are needed. In each iteration, as each executor sends current segment to its succeeding executor, receives the segment from its preceding executor, and merges the segment to the next segment. In fact, the communication amount can be further reduced by in-memory merge. Conventionally, Spark requires tasks to be independent. Thus, Aggregators will be serialized and write to disk by the block manager, even if they are on the same executor. With in-memory merge, those aggregators on the same executor will be merged into a shared aggregator. Driver notifies executor to serialize and write a shared aggregator when the stage completes. Then we will present the evaluation results. The experiment configuration here is the same as motivation. The communication latency versus message size figure reveals that Scalable communicator has near MPI performance and has significantly lower latency than Spark Block Manager. The communication throughput versus message size figure reveals that, unlike MPI, only with parallel directed ring can the Scalable communicator fully utilize the network bandwidth. This is due to high CPU overhead from Java serialization and deserialization. The reduced scatter time versus number of parallel PDR rings reveals that parallel directed ring improves the reduced scatter performance, and topology awareness further improves the reduced scatter performance. The reduced scatter time versus the number of executors figure reveals that the reduced scatter performance of a scalable communicator is as scalable as MPI, even goes beyond MPI. This figure compares tree aggregation with in-memory merge, and split aggregation with in-memory merge. For large messages, in-memory merge improves aggregation performance, and split aggregation further improves the performance. For small messages, the performance are similar. The speed up of end-to-end MLlib applications shows Sparker improves the end-to-end MLlib distributed machine learning training performance. The strong scalability of LDAN on AWS reveals that Sparker improves the end-to-end MLlib distributed machine learning training strong scalability due to improved reduction performance. In summary, we propose an aggregation interface for distributed datasets that supports scalable reduction, develop a low latency and high bandwidth communication layer integrated into Spark, and improve the end-to-end scalability of Spark distributed machine learning. That's all for the representation. Thank you for your listening.